bell's gonna ring in a couple minutes, so I'm gonna try this anyway, and then we'll just go from there. So what we're gonna focus on right now is this statement right here. It says that given an angle and the angle bisector, any point on the angle bisector has equal distance to the angle sides. So here's my angle bisector on that diagonal. And the question is, what does it really mean to say that this point here has a distance to either one of these sides? Like, what does distance like that mean? And it seems kind of abstract, but you actually know the answer to this. If you're a runner in a marathon or just a race, and here is the finish line, what's the distance, right? Is it going to be this line on the, like, can you see that? I don't know. Like, is it this distance right here? Is it this distance that's kind of smaller? Or would it be the distance that goes straight from you to the finish line? So that's what that is. It's this distance straight from you to that finish line. And specifically, when that happens, you have a right angle. So it is the shortest distance from you to whatever that line is. And when that happens, that line turns out to be perpendicular to you and the finish line. And so what we do is we take this point right here and we draw the perpendicular line from this edge to that point. And so I'll do it right now. Estimating, it's going to be that dot. I need it bigger. It's going to be this line right here that's perpendicular. And then it's going to be over here that's going to be perpendicular. And so that's where you see the right angles come in. So really, what's happening is that we have an angle bisector here. And it's a bisector because we have two wedges in that sense. Okay. And they are equal. And so this dot here has equal distance to this line. Sorry, this dot here has equal distance to the left line as this dot here to the right line. And that's where the 90-degree angles come in. But really, we're just setting these two pieces equal. So 4x plus 7 equals 5x minus 16. So what x equals 23. In this situation, we have 15x plus 31 equals 21 minus 10x. And so 10 equals 25x. So x equals 2 over 5. Pretty easy. What that again leads to is the incenter. So what I've drawn for you here, and I don't want to make a whole fiasco out of the diagram, are the angle bisectors of x, y, and z. And like yesterday, they're going to be concurrent at a single point. So angle bisectors, they are concurrent at a single point. That is the incenter. Now the incenter has equal distance to all sides of the triangle. And so from C here, from C here to that side there, it's the same thing from C to M, and the same thing from C to N. From C to L, M, and N, those are equal. And these are the distances to the sides because these are the only lines that are perpendicular to those sides. But that's the reason why these right angles come in. That expresses to us that this line here truly is the one that goes straight to that side. It's not something that's lopsided, like going from here to there. That's crazy. Okay. And so we have to shift our mindset. In this setup here, we are looking at the incenter, and that turns the in radiuses right here. And so we are focusing on that's wrong. That's weird. Okay. So we have the in radiuses, which is here, here, and here. Okay. And these are the ones which are congruent. And so if this one's 60, that one's 60, this one is 60. In fact, the sides here do nothing. They're just there effectively for decoration. There's nothing like really special there. And moreover, What we have here are there are three right angles there. In fact, the incenter is in a sense a little bit easier because there's not much to label. This line here is equal to this line here is equal to that line there. And so they are all 60. And like we talked about yesterday, in each region, so this region here, this region here, this region there, those triangles are going to be equal. And so, I mean, here's how to start. You pick out a triangle in each region, and then you keep doing your own little thing. So here's one I'm going to pick out. Here's a second. And then here's a third. And so I'll label this as 1, 2, 3. And again, Pythagorean theorem comes into play. The pair of triangles are the same, so if this is 11, then this is 11 as well. So we have what? KH squared equals 11 squared plus 60 squared. So 11 squared plus 60 squared. We're going to square root that answer, 61. So we found this one right here, and we've solved those pair of triangles. Cool. Move on to triangle number 2. Again, we know that this is 32, so this one is 32. And so now I have a triangle with 2 of the 3 sides. I can solve for it. So in this situation, we have 60. Hold on. This is ki. So ki squared equals 60 squared plus 32 squared. Da 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 da. Oh, that's going to be a big number. Fingers crossed. Thank God. Okay. So ki squared equals 4624. And so when we take that square root, ki is equal to 68. Cool. And then lastly, in triangle number 3, we have this as 25. So we're going to copy it over here as 25 as well. So what, 25 squared plus 60 squared is 4225. Square that answer, that's going to be 65. So 25 squared plus 60 squared equals jk squared. And so 4225. And we are done. So what's similar between incenter and circumcenter problems are the fact that we just have 3 smaller Pythagorean questions. That's it. So let's try this one more time in this diagram here. Notice that the incenters, the in radii, are here, here, and here, and we are not given them. Pause. We're going to separate out the 3 triangles that we're going to use. And notice that the right angles go here, here, and there. And so the first objective in any of these questions is you're going to have to find the incenter, or I'm sorry, the in radius. So number 1, we're going to find and label all in radii. And like the last section, we're going to use the triangle with 2 known sides. And so we have to use this triangle first. And it's a matter of choice for which triangle we use second. So I'll do that one second and that one third. So triangle number 1 here tells me that WK squared, nope, my hypotenuse is actually 25 squared, 7 squared plus WK squared. We're going to subtract out that 7 squared, which is 24. I think it's, If you're wondering how I knew that, Pythagorean triples. I just happen to know that 24, 7, 25 was probably one of them. But anyway, WK equals 24. And so that is my value for all three of the in radii. So this is 24, cool. But to make progress on this problem, you label all the other in radii as well. And so triangle number 2, I'm trying to find VG right here, but 32 is my hypotenuse. And so we have 32 squared, so I'm going to do it over here. 32 squared equals 24 squared plus VG squared. We're going to subtract off 24 squared. So 32 squared minus 24 squared. That's, ew, that's not a perfect square. Let me check. Yeah, no. Okay, so 448. Let's divide that by what, 8? Let's do better. 64? Oh, great. Okay. This is 64 and 7. This is going to be 8 and 8. That's already a pair. 7 doesn't factor. So VG comes out to be 8 square root of 7. Great. And so that is exactly what WG is as well. 8 square root of 7. In fact, this one over here is 7. Okay. Last but not least, we have this triangle on the bottom that we have to find UH for. So we have 24 here, 26 there. We'll find UH. So triangle number 3, hypotenuse is 26. Subtract off 24 squared. UH squared. Oh, 100. That's cool. The square root of 100 is just nice old 10. And so we are done here. Okay. WG is 8 square root of 7. KV is 24. FH, where's FH? FH is, oh, okay. So UH here is 10. So FH is 7 plus 10, that's 17. And WK is 24. And that concludes this lesson here. Thanks.